Good afternoon, everyone. I'm Xinchun Hu, come from HUST. I'm just graduated from HUST, and now I'm a new member of Tongli University. My supervisor is Yang Wang. Today, my report is Joint Detection of Massive Black Hole Binaries by LISA and TianQin. From this GW spectrum, we focus on low frequency gravitational wave detection, which the frequency is 10 to -4 to 1 Hertz. In this frequency band, there are abundant astrophysical sources, such as massive black hole binaries, galactic white dwarf binaries, and some extreme mass ratio inspirals, and some stellar mass black hole binaries, only in spirals. In those sources, we only focus on the massive black hole binaries. LISA and TianQin are two typical space-borne detectors. This slide shows the LISA and TianQin constellation. Here, I will not introduce the LISA and TianQin orbits in detail because I believe every one of us is familiar with them. The most famous massive black hole is with 4 million solar mass in our galaxy center. It is deduced by detecting the multiple stars for decades. And the observational evidence also shows that each galaxy has a massive black hole. When two galaxies merges, the massive black hole will enter the newly formed galaxy due to the dynamic friction and forming a massive black hole binary. There are also some massive black hole binary observational evidence, such as OJ287. The study of TianQin scientific goals shows that TianQin can detect massive black hole binaries with the redshift up to 30, and with the optimistic massive black hole binary model, TianQin predicts that it can detect about 60 massive black hole binaries per year. The research of the TianQin massive black hole binaries scientific goals promotes us to do the TianQin massive black hole data analysis. However, we need to deal with the laser phase noise. Firstly, the reason is that the arm length of the space-borne detectors are not equal due to the perturbations from other planets. So the time delay interferometry method, short as TDI method, is proposed to cancel the laser phase noise. The main idea of the TDI is to construct the vertical equal arm length to canceling the laser phase noise. Here we show the typical optical paths corresponding to the TDI combinations. On the other hand, LISA code also demonstrates the validity of the TDI to cancel the laser phase noise. Here, the red line represents the raw laser phase noise. It is 7 to 8 higher than our GW signal, and the black lines represent the secondary noise, and here is the GW signal. We called the data processed by TDI as the scientific data. Next, we will take the TDI-X combination, for example, to do the massive black hole data analysis. This slide shows the massive black hole binary inspiralling waveform. This is the orbital frequency up to the 2 p.m. The GW phase can be integrated by the orbital phase in this expression. From this GW waveform, we can find that a massive black hole binaries can be determined by these 9 parameters. They are collision time, total mass, symmetric mass ratio, and sky location. This is the luminosity distance. This is the angle of line of sight and the initial phase. And this is the polarization angle. On the other hand, TDIX noise, PSD, can be expressed by this expression. From this GW model and TDIX noise model, we can do the data simulation. The first one, we show the noise simulation results. We can find that the simulated noise satisfies the TDIX PSD. On the other hand, we also HUST the time domain noise. We can find that the simulated noise satisfies the Gaussian noise. So this is the noise simulation. In terms of signal simulation, massive black hole merge may be outside or within the observation window. We call them case A and case B. This is the TianQin data simulation. In the real data analysis, we input this signal into 20 different noise realization to generate 20 size data. We do data analysis for this 20 size data. In order to do the joint detection, we also simulate this massive black hole signal for LISA data. We show this frequency domain data. In case A, LISA with SNR is 277, and TianQin with the SNR 124. In case B, LISA SNR is 142, and TianQin SNR is 117. We call case A and case B for high SNR case later. Based on the maximum likelihood ratio, based on the maximum likelihood estimation and F statistic method, we use the particle swarm optimization algorithm, short as PSO algorithm, to maximize the maximum likelihood ratio function, which is the function of the intrinsic parameters. We show the PSO search results of the intrinsic parameters. Here the red dashed line represents the true parameters of the intrinsic parameters, and the black and the blue line represents the search results. We can find that the search results is very close to the true parameters. We also use this searching results to recover the GW signal. We also calculate the fitting factor between the recovered signal and the template. The fitting factor can all reach 99.9% for both LISA and TianQin. On the other hand, we also compare the signal residue with the template. The PSD has decreased 3 to 4 orders of magnitude. We can conclude that PSO algorithm can give accurate parameters estimation. This is the case A results. For case B, we can get the similar results. The fitting factor can also reach 99.9%. In order to study the source localization, we also simulate a low SNR case labeled as case C. In case C, the LISA SNR is 37 and the TianQin SNR is 3.9. If we assume the space-borne detector's threshold is 8, it means that TianQin cannot detect this massive black hole signal alone. We want to study the contribution of this dim signal from TianQin in the joint detection. The first step is to do the data analysis, just like in the case A and case B. We can find that the fitting factor has decreased. This is the reason is that the SNR in case C has decreased. Finally, we study the source localization for high SNR and low SNR respectively. In the case A, for the high SNR case, we can find that the source localization searching results only converges to the true position and the symmetric position. We calculate the variance near the true position and the symmetric position, labeled them as sigma theta, sigma theta 1, sigma phi 1, and sigma theta 2, sigma phi 2. On the other hand, we convert this symmetric position to the true position to get the total data. And we calculate the total data variance labeled as sigma theta, sigma phi. We finally conclude that the source localization uncertainty of joint detection has improved about 3 orders of magnitude than LISA alone. This is the conclusion for the high SNR case. In the low SNR case, case C, we following the same method to calculate the variance. The conclusion is that the localization uncertainty of the joint detection has also improved 2 times than LISA only. This means that the sources cannot detected by one detector can also contribute to the joint detection. These results also proved by the ground-based detectors. Okay, that's it. That's all. Thank you for your listening.
Thank you very much. That was very interesting. Do we have any questions for Xinchun here?
I do have a question. So Xinchun, can you go back to just slide 13? I'm looking at the sky localization ability number, which is a bit strange that with SNR of larger than 100, usually you would expect much better sky localization ability than several hundred of square degrees. And why is that for LISA alone, the sky localization is as large as, say, 253 or 353 square degrees?
You mean the SNR for 100, the sky location with 253 is better than this one?
No, I'm just saying that I wouldn't expect the SNR larger than 100 or as high as 37. I wouldn't expect the sky localization to be as bad as several hundreds of square degrees. Is there a physical explanation for this bad sky localization?
Sorry.
Maybe I can just ask in Chinese. 我问的问题就是信噪比这么高的情况下，为什么这个在单个探测的时候，空间定位能力这么差？有没有物理的解释？这边？
你说的是单个 LISA 这种
Yes. So maybe you can try to respond in English, maybe, if that's possible.
Sorry, maybe I need to refer more reference to check this result.
Okay.
So
no
Xinchun,
worry.
actually, sorry for interruption. So Xinchun, do you have the backup slides for your sky localization map? Even the other parameters are fixed as true parameters?
Maybe in this slides yeah.
Hi, Xinchun. Okay.
Yes, we can hear you, Zhengcheng.
I have a question that do you consider prospect in your no? Do you consider the foreground in your work? And if you do so, does it make a big difference to your results?
We didn't consider the foreground. We only consider the secondary noise, such as the acceleration noise and short noise.
Okay, I see.
Yeah, we also we want to consider the foreground for the next step.
Okay.
By the way, for the slide 12, I've got another question on the PSD. If you can go to slide 12. So I didn't quite, well, maybe okay. 12, yes. I'm just looking at the PSD at low frequency. So it's logarithmic in base 10. So this is 10 to the -5, 10 to the -4 hertz, and we are seeing it to be flat. And why is the noise flat in this regime?
This is the TDI-X noise PSD, just like this expression. This expression, and the short noise is not the frequency function. So the
short noise should be frequency independent. The acceleration noise should be frequency dependent. So that's a bit strange to me for this for slide 10 and slide 9 and slide 12. Maybe there's something that you didn't cover or I didn't get. I'm pretty sure you did it well.
You can refer. You can refer to the TDI-X PSD reference. They have the different TDI-X TDI combination PSD figure. This is in the low frequency. It is frequency independent.
Okay, I'm sorry. Can you hold this for a second? This is slightly strange to me. The equation, sorry, the slide 7, I believe you were showing the equation slide 7. it seems there is a typo in page 7.
7.
Yes.
Yeah.
Here. So for example, you look at the TDRX noise PSD equation is showing in the very last line, the two terms inside the bracket seems to be have, oh, sorry, my fault. Forget it. No, it's okay. Sorry.
So
Thank
actually,
you. Are there, yeah, sorry, Jan, go ahead. Jan, did you want to say something?
yes, I was thinking also the same question as Yiming was thinking about the noise PSD on page 7. I guess in the acceleration noise, we usually reference it to as f minus 1, f to the power of minus 1 in the amplitude spectral density. But here, I guess maybe maybe f to the minus 2. Here, maybe because of this expansion of sine functions in the low frequency frequency domain, then that maybe the contribution from the positive f's will cancel partially the negative f's in this acceleration noise, especially it is expressed in a term that is as relative frequency changes rather than the usually we reference to the string changes, delta L over L or delta nu over nu. So the shape of SY acceleration noise would be different by maybe by a power of F. If we talk about amplitude spectral density, maybe a power of F square for the power spectral density. So, but I guess maybe it's worthwhile for Xinchun to double check if noise PSD using here is consistent with other literatures, so that there is no other maybe some sort of climbing of this tail in the lower frequency domain.
Okay, I will check it after.
Okay, thanks.
Thanks. Good stuff.
Excellent. Thank you so much, Zhengcheng. I think we should all say thank you to Zhengcheng and move to the next talk.
Okay, thank you.
So Zhengcheng, thank you. Zhengcheng, it's your turn now. So yep, there you go. So take it away.
Hello everyone, I'm Zhengcheng from TianQin Research Center for Gravitational Physics, Zhangjiang University. My supervisor is Xinchun Hu. My report is science with the TianQin Observatory preliminary results on stochastic gravitational wave background. So far, the ground-based gravitational wave detectors have detected 52 events. In addition to these observable sources, there are also a large number of events cannot be detected individually. As shown in the figure, the incoherent superposition of the signals forms a stochastic gravitational wave background. Generally speaking, the origin of stochastic gravitational wave background can be divided into two categories. One is the astrophysical origin, such as binary black holes, binary neutron stars, and other binary star systems. The other is the cosmological origin, such as inflation, first-order phase transition, and cosmic defects.
没事，我去看看。这是我们组，所以说不用着急。
we usually adopt omega GW to denote the strength of the stochastic gravitational wave background, which represents the ratio of stochastic gravitational wave background energy density to the critical density. And using the equation in the last line, one can convert omega GW to the power spectral density SH. When such a background is higher than the detected noise, it becomes the foreground, which is expected to be generated by the double wide dwarf in our galaxy. The figure shows the power spectral density SH foreground for different operation times within TianQin. As the time increases, more gravitational wave can be identified separately to lower the foreground. That is to say, with more observation time, the foreground grows weaker. LISA will operate at the same time as TianQin, which these are two remarks that what the joint observation of TianQin and LISA would bring to the foreground. From this, we propose the joint foreground for the first time, and similar to the effective noise of multiple detectors. The joint foreground of TianQin and of TianQin plus LISA is shown in the figure. The number of resolvable sources is increased, and the joint foreground is further depressed. We mentioned TianQin plus LISA as shown on the right. It can be seen that TianQin is orbiting the Earth, while LISA is in the orbit around the Sun about 20 degrees ahead. Besides, my work also involves TianQin and TianQin 1 plus 2. On the left, both TianQin and TianQin 2 orbit the Earth, and their orbital planes are perpendicular to each other. The next step is to introduce the methodology. The stochastic gravitational wave background is submerged by detected noise. We need to adopt special detection methods to extract it. The first method is correlating the background in the two noise-independent channels. This method is therefore called cross-correlation. However, for a single triangle space-borne detector, such as TianQin or LISA, this method loses efficacy. People then put forward the null channel method. The null channel is a signal-insensitive channel, of which the noise is related to the detection channels. Thus, the background can be extracted from the detect channel when the null channel is used as the noise monitoring. This method demands us having a full understanding of the channel noise. In order to properly calculate the SNR, we need to define the overlap reduction function, which represents the correlation between two between channel data. Based on overlap reduction function, one can calculate the SNR through the power spectrum density of the, the stochastic gravitational wave background and the channel noise. It can be seen that the SNR is related to the total observation time and the detection frequency band. With the tools in hand, we can then ask what is the expected SNR for given sources. First, we need to calculate the corresponding spectrum of stochastic gravitational wave background. In this figure, we show the background of binary black holes, binary neutron stars, and massive black hole binaries. That spectra can be obtained by the space integral of the merge rate and the energy spectrum. We adopt the merge rates of binary black holes and binary neutron stars predicted by gravitational wave events. As for the massive black hole binary, its spectrum is weaker in the TianQin frequency band. In order to show the influence of foreground, we convert the foreground power spectrum density SH to the green dotted line. It can be seen that the background will be covered by the foreground near the millihertz band. Then is the cosmological origin. For the primordial gravitational wave produced by quantum fluctuation during the inflation, first order phase transition resulting from bubble collision in very early universe, and the cosmic defects corresponding to the topological defects of the universe. We select the spatial parameters to calculate the spectra. In this figure, the spectra of phase transition and the cosmic defects are stronger than the astrophysical origin. On the other hand, the primordial gravitational wave produced in a single inclinationary field would be much weaker. To evaluate the detectability, we also need to obtain the detection sensitivity of configurations. As shown in this figure, the red, green, and blue line denotes the power law integrated sensitivity curves of TianQin 1 plus 2, TianQin plus LISA. Note that the effects of observation time and SNR threshold are considered, corresponding to the 1 year operation time. We adopt the observation time of TianQin and TianQin plus LISA are half a year, and of TianQin 1 plus 2 is 4 months. With the background spectral shown on the left, combined with the sensitivity of these configurations, the SNR is calculated in the right table. We take the example of the binary black hole, binary neutron star, and the first order phase transition. One can find that the SNR of the cosmological origin is very large, which is due to the high uncertainty of the cosmological models. We select some specific parameters to obtain the optimistic results. On the other hand, the SNR of null channel is higher than the cross correlation. As mentioned above, the null channel method demands us having the recognition of the channel noises, and the cross correlation is the more feasible method. Finally, some conclusion. The foreground of TianQin is below the detected noise after 5 years of observation, and it is further depressed by the detector network. We can adopt null channel or cross correlation to detect the stochastic gravitational wave background with the space-borne detectors. The stochastic gravitational wave background that is expected to be observed by TianQin include astrophysical and cosmological origin. Thank you for your attention.
Thank you very much. Do we have any questions? Okay, then I have a question. So in your talk, you obviously for trying to observe the primordial signals, you need to have some sort of template or idea of what the signal will look like. Are there many, I guess options might be a word, are there many different variations to what you think the signal will look like? Or is there one that is definitely what the signal is expected to look like? If that makes sense.
I think you mean the uncertainty of the cosmological source is affects the strength of the stochastic gravitational wave background.
Well, it's more to do with every time before we detect something, there's the expected signal or what it would look like. But of course, until we detect it, we don't really know if that is for sure what the signal looks like. So there tend to be templates, as far as I'm aware, for detecting all these various signals. So for the primordial, is that the same way? Or do we know for sure, like this is what it has to look like? Or are there many different templates for the signal, and so you account for all of them in your calculations?
To be honest, I cannot understand what do you mean, but what I can...
I can translate into Chinese, and maybe you can try to respond in English. So,
Okay.
Thank you.
那个问题是说，通常引力波的探测啊，需要用到模板啊，对。然后，但是呢，就是他就问说，对于这个你现在讨论的这个早期起源 primordial 的这种起源的，它是不是需要模板？然后需要的话，你这边手里面要有多少种模板，然后可以把这不同的信号给区分开，是这样的一个问题。
OK， 其实我大概是听懂了些，但是不确定是不是这个意思。我听到模板，但是对 OK。In my opinion, the primordial gravitational wave is composed of a large number of the gravitational wave signal produced during the inflation, and I think there is no template, so-called templates in my calculation, because introduce first the stochastic gravitational wave background is the incoherent superposition of large number of the signal. Yes. So I think there's no template in the primordial gravitational wave calculation, and what we can do in the calculation is, I see. You can find this equation to calculate the omega GW of primordial gravitational wave, and it is related to the omega radiation and some specific parameter. So I think I do not answer the question for more. Yes.
Okay, on top of what Zhengcheng mentioned, I think Zhengcheng is covering more on the astrophysical or cosmological, or in another word, the theoretical side of the sources, while I think Mariella is asking about more on the data analysis part, right? So I think this stochastic signal is quite different than any other sources in the sense that the detection cannot utilize the method of template-based technology. This is simply because the signal we are talking about behave in a way that's very similar to a noise. And we have to rely on the identification of the spectrum for the signal to tell that there exists such source. I hope this can resolve the issue that Mariella was asking about.
Yeah, definitely. Thank you, Yiming, and thank you, Xinchun. Are there any other questions?
I have a question.
Go ahead.
Thanks. So, very nice talk for both speakers, actually. And sorry I'm late for the beginning. I'm just looking at this slide now, and there's this model here, I think for cosmic strings, the red line, basically, that seems to predict a very strong background. Can you say something more about this?
Okay. When we calculate the stochastic background of the cosmic string, we adopt the specific parameter to obtain the optimistic results. As you can see that if you choose some different parameters, you can get a lower background. This result is the optimistic result. I think.
Okay, thank you. But just to follow up quickly, is the optimistic result, because there are some limits, constraints put on the parameters of strings. Is the optimistic result still allowed by the constraints?
I think we can do that. Yes, and for the phase transition, for the first order phase transition, we do the same work by the SNR contour figure to constrain the parameter.
Hi,
and
so maybe I can follow on that. Currently, I think the constraint on these parameters are very poor, so that it leaves us a lot of freedom to explore. So all the parameters we choose in this plot are all allowable by current experimental constraint. So people, like normal people, would not expect very high amplitude, but still it is not excluded by current observation.
Okay, thanks, Yiming. And thanks to Zhicheng.
okay.
Excellent. Are there any more questions then?